I'm here to present in the platform engineering for FinTech. We want to specifically discuss about database architecture in FinTech and how this distributed database sharding works, replication and scaling, and how it helps the FinTech industry. As we all know, modern FinTech platforms require platform engineering solutions that can process massive transaction volumes during peak events in milliseconds while maintaining the accuracy, also the availability. So, as financial services scale globally across different regions and environments, which have different regulatory requirements, platform teams must architect distributed database system that supports retail banking, trading, digital wallets, and payment processing at unprecedented volumes. So the agenda of this PPT is split into the 6 parts. First, we will discuss about the platform engineering foundation, how it evolved around the financial infrastructure, how the requirements are captured and scaled, and what is the role of a database architecture here. Then we will look at deeply into the database strategies. We will start with the database sharding strategies. We have a different sharding strategies like horizontal partitioning, geographic or regulatory sharding, and operational management. Right. So there are replication models which can be synchronous or hybrid, whichever suits for the financial tech industries. And consistency models, strong consistency, eventual consistency, and casual consistency for different financial contexts. So then the architectural patterns, how these database driven architectures are used, like event driven architecture, microservices, CQRS, and event sourcing. Then we will look at some case studies and future directions where this platform at FinTech goes with respect to database and especially distributed database. So let's dive in. As evolution of financial infrastructure, we know the financial industry has undergone a significant transformation over the years on how it approaches the data management and system architecture. Right. So, for example, traditional banking system built on monolithic architectures at first have given way to distributed systems and cloud native platforms. Recently, platform engineering has emerged as a critical discipline focused on creative self-service capabilities. Modern fintech platforms face multifaceted challenges requiring horizontal scalability while maintaining the asset properties, which is critical for fintech industries. High-frequency trading system must process market data and execute trades within microseconds. Digital banking platforms need to handle millions of simultaneous users at a time. Payment processors must validate and settle transactions across multiple currencies and different countries and which have a different regulatory jurisdiction while maintaining the perfect accuracy. So this is our evolution of the financial industry over the years and the need. Now we will understand the scale requirements, right? So accuracy and auditability. Financial transaction demand absolute accuracy, auditability, and permanence. Zero margin for error is acceptable in calculation, and comprehensive logging is mandated by regulatory requirements. Extreme usage spikes. Financial platforms must adeptly handle extreme usage spikes triggered by market events, product launches, or seasonal activities like tax season or high trading day, and due to global events. The architecture must ensure consistent performance through robust auto-scaling capabilities. And there is geographical distribution comes into play as well because we have to comply with the data residency laws across diverse jurisdictions of different countries, coupled with the need for low latencies, global access, mandates multi-regional database deployments for financial services. With these in mind, the database from monolithic evolved into distributed database in the fintech industries, and it is playing critical role in serving the consumers as well as keeping the regulatory requirements. Right. So we will look at the different strategies involved in this. First, the sharding strategies. So under the sharding strategy, the horizontal partitioning in financial context. Right. By distributing data across multiple database instances, sharding enables linear scalability while maintaining the low latency query performance. The primary challenges lies in maintaining the transactional integrity across shard boundaries. So user-based sharding is one of the most common in financial platform because this partitioning based on user data or account number can be executed or operate within the single shard, and all the information can be in single shard of a particular user. However, operations spanning multiple user accounts like payment from one account to another, which involves different shards, require sophisticated distributed transaction management to maintain performance as well as consistency. So there is also a geographic and regulatory sharding. First thing may be a regulation regional compliance is required. Right? Geographic sharding enables that strategy enables that regulatory requirements. It aligns the database distribution with the regulatory requirements, ensuring customer data remains within specific geographic boundaries. Right. So then it also enables a cross-border transaction. If you have a geographic sharding, payments between regions involve data stored in different geographical shards require complex routing logic and transaction coordination protocols. Time-based sharding. Historical transaction data is critical in fintech for the statements, tax purposes, and others that can be partitioned by date ranges, enabling efficient archival and compliance reporting while keeping recent data in high-performance shards. Effective shard management requires automated tools and processes that handle operational complexity, including monitoring systems that track shard performance metrics and capacity utilization. Shard rebalancing represents one of the most complex operational challenges as user bases grow unevenly or transaction pattern changes due to various reasons. So the next one is the replication models for high availability. So the replication models can be asynchronous or hybrid. We will look at the synchronous replication first. Synchronous replication for financial accuracy. Synchronous replication provides the strongest consistency guarantees, ensuring all replicas contain identical data at any point in time. This is essential for critical financial operation where inconsistencies could result in financial losses or regulatory violation. Right operation must be confirmed by all replicas before the transaction is even considered complete. Ensure any replica can immediately take over without data loss during primary failure. Introduces additional latency and complexity due to this, especially when it is across different geographical location. Also, multi-master synchronous replication presents additional complexities in while doing the conflict resolution. So then there is an asynchronous replication enables financial platforms to achieve global scale while maintaining acceptable performance. The operations are committed to the primary database and then propagated to replicas asynchronously. It reduces the write latency significantly and enables geographic distribution of read operations easily. Introduce possibility of temporary data inconsistencies between replicas. Requires careful monitoring of replication lag, needs sophisticated conflict detection and resolution mechanism if you are using asynchronous replication, which is the downside. Hybrid replication strategies. Modern financial platforms often implement these kind of hybrid approaches combining synchronous and asynchronous replication based on data classification. So this gives benefits of both worlds. Financial data uses synchronous replication within a region and asynchronous across region. Less critical data may use asynchronous replication exclusively, requires sophisticated data classification and routing system. Application must handle different consistency models for different data types. So then there is the consistency models in financial system. There is strong consistency, essential for core banking system, trading system, and payment processing where accuracy is paramount. All nodes see the same data at the same time. Requires sophisticated coordination protocol, prioritize consistency over stability. Eventual consistency, better performance for analytics, reporting, and customer-facing application. Rich temporary inconsistencies require conflict resolution mechanism, needs monitoring for replication lag. Casual consistency. So it's a middle ground for complex financial workflows, ensures casually related operation maintain order, allows unrelated operation to can be reordered, requires timestamp and dependency tracking. So moving on to the next topic, which is architectural pattern for financial scalability. First architectural pattern we can take as event-driven architecture. It is essential for building scalable financial platforms that handle complex multi-step processes while maintaining loose coupling between services. Event sourcing provides complete audit trails for regulatory compliance, requires careful attention to event ordering and delivery guarantees. Event streaming platforms like Kafka have become central to many financial architecture for this reason. Microservices architecture is paramount for any org, but it is more paramount to financial fintech org as well. It enables financial problems to organize complex business logic into manageable, independently deployable services. Domain-driven design helps identify appropriate service boundaries, requires sophisticated transaction management across service boundaries. Service mesh technologies provide essential capabilities for security and monitoring. Then we have CQRS, command query responsibility segregation, which separates command processing from query processing, optimizing each for specific requirements. Write operation focus on maintaining consistency and business rule, while read operation optimize for performance and user experience. Enables specialized read models for different use cases. Then there is event sourcing benefits. It complements the CQRS by providing reliable mechanism for propagating state changes. Events generated by command processing update read models asynchronously, provides natural audit trails for compliance, enables creation of new read models from historical event streams, requires sophisticated event processing pipelines to implement this. Then there is an important topic in the fintech industry, which is always a talk, security and compliance, which is critical for the fintech industry while maintaining the customer data and information. So there is an encryption and data protection. Financial data requires protection both at rest as well as in transit. Transparent data encryption are for stored data, secure communication between all system components, hardware security models for key management. Access control, fine-grained mechanism ensure data is only accessible to authorized user, role-based and attribute-based access control, MFA, multi-factor authentication for sensitive systems, row-level and column-level security policies also being implemented in various places. Regulatory compliance, financial platforms must comply with numerous frameworks, data residency requirements, privacy regulations like GDPR, detailed audit logging and reporting capabilities for tax purposes and others. So we will look at the case studies, real-world implementation, high-frequency trading platform. Major investment bank implemented distributed architecture requiring microsecond latencies and perfect consistency, geographic distribution with co-located databases instances, hybrid approach, which we discussed in the previous slides, combining synchronous replication within region and asynchronous across different region, sub-millisecond performance monitoring with automated resource allocation. Digital banking platform, leading digital banking platform built globally distributed architecture supporting millions of customers, sharding strategy based on geographic location and account type, event-driven architecture with comprehensive event sourcing, eventual consistency for user experience and strong consistency for financial operations, money transfer and stuff. Payment processing network, global processor handling peak volumes with sub-second authorization times. Combination of geographic and merchant-based sharding, which is user-based sharding, real-time fraud detection with machine learning, disaster recovery, redirecting, reprocessing within seconds. So where the future heads to, right, with all this stuff in financial platform engineering, cloud-native database technologies, right, the evolution towards technology designed for distributed containerized environment, serverless database eliminating operational overhead, multi-cloud strategies balancing performance, cost, and compliance, integrated security and compliance capabilities. Also, as talk of the town, there is an AI and ML integration as well and quantum security, right? Transformative capabilities being integrated directly into database system, automated performance tuning and anomaly detection by AI, real-time fraud detection and risk assessment, quantum-resistant cryptographic algorithms is being researched, and hybrid security approaches during transition period. So that's all for the presentation today. Thank you. Thanks for listening to this.